In this video we're going to talk about direct proofs. This is the most common type of proof that is used, I would say. And so in a direct proof we're trying to prove a statement that has a hypothesis and a conclusion. And the strategy is, again, I think it's obvious once you think about it. What we're going to do is we're going to assume or suppose that the hypothesis is true. We're going to give that to ourselves to work with, and then we're going to use it, and we're going to argue that the conclusion has to be true. So you sort of fill in the space between the hypothesis to the conclusion with logical arguments. You get from the hypothesis to the conclusion. Okay? Okay, so here's a first example. If n is an odd integer, then 3n plus 7 is even. So we're going to prove that. Now, one thing that's really important when you're doing proofs is to be absolutely precise with terminology and to use the definitions exactly. So odd and even, right? So as a prelude to this, we need to be very crystal clear in our minds what an odd integer is and what an even integer is. So let me just write that in. An integer m is even if m equals 2k for some other integer k. That's the usual definition of an even number, right? It's 2 times something, right? And an integer m is odd if m equals 2k plus 1 for some other integer k, right? So basically 2 times something plus 1. These are the usual, there are other ways to write it, but these are the usual definitions of even and odd. Okay, so now back to what we're trying to prove. If n is an odd integer, then 3n plus 7 is even. So our hypothesis is that n is an odd integer, right? So we want to say, suppose n is an odd integer. We're allowed to start with that. That's the hypothesis. And now we have to argue to 3n plus 7 is even. All right, so that's where we want to end up, saying 3n plus 7 is even. All right, well, n is an odd integer. We get to use the definition of odd. So this used m, but our number is n, so we just want to change m's to n's here. So n equals 2, and I can use k, 2k plus 1 for some integer k. All right, so we've used that definition. Obviously, we needed to use that. It must be important that n is odd, or it wouldn't be in the hypothesis. So we've used that. Okay, so now let's move on to the 3n plus 7. Then 3n plus 7. And we want to prove that it's even, so we ultimately want to prove that it's 2 times something, right? Well, how do we get there? Well, we have something that n equals 2k plus 1, so we can sub that in. So 3 parentheses 2k plus 1 plus 7. Now there's some obvious algebra I can do, right? So that, what does that turn into? That's going to be 6k plus 3 plus 7. So 6k plus 10. 6k plus 10. And algebraically, that's the simplest way to write it. But remember, I need to write it to show to anybody reading this that it is an even number. I need to write it as 2 times something, some integer k. In my case, I can factor out a 2, and what's left is 3k plus 5. I don't really care what's in the parentheses. That is just some other integer. I mean, it's at least an integer. I guess you do have to make sure, you have to confirm to yourself that if k is an integer, then 3 times it plus 5 is an integer. Of course it is. So my point is that it's 2 times something. Thus, 3n plus 7 is even. And so we got to the conclusion. We started with the hypothesis. We used definitions, both of odd and then of even, to show that 3n plus 7 is even, which is the conclusion. So we're done. Okay, here's another one. Again, using odd and even, in this case odd. The product of two odd numbers is odd. Okay, so we want to prove that the product of two odd numbers is odd. So this one is a little bit tricky to identify hypothesis and conclusion. I think the hypothesis here is that we have two numbers that are odd. So in other words, I guess I could rewrite this, I could reword this sentence in an if-then format. I could say, if two numbers x and y are odd, then x times y is odd. And then it's more clear what the hypothesis and the conclusion are. The hypothesis is the if part, and the conclusion is the then part. In fact, maybe I'll just write that here. If x and y are odd integers, then xy is odd, right? It's the same thing, but now it's clear what the hypothesis and the conclusion are. We kind of had to introduce variables to rewrite it that way, and that's good because that's what we're going to need to do in a proof. So here's our direct proof. So suppose x and y are odd integers. So we eventually want to say that x times y is odd. That's going to be like our last line of the proof. xy is odd. Now we have the definition of odd. Odd means 2 times an integer plus 1. So since x is odd, I can write x is 2k plus 1 for some integer k. And now y is also odd. So I'm going to write and y equals, now I have to be careful here. It can't be the same k. It's not necessarily the same k, but it's 2 times something else. I'll just use L plus 1 for some integer L. Now I would probably, this is not necessary, but I would probably kind of rewrite this in a more natural way. I'll say, so x equals 2k plus 1 and y equals 2l plus 1 for some integers k and l. Just a little bit smoother way to write it, right? So, okay, so we've used the definition of odd and we have expressions for x and for y. Okay, then now let's see what xy gives us. X times y. We want to ultimately show that it is odd, so we ultimately want to say that it's 2 times something plus 1. Okay, well, we can sub in our expressions like that. I think the obvious thing to do here is multiply it all out. So we get 4kl plus 2k plus 2l plus 1. And we want to make it obvious that this is 2 times something plus 1. Well, we got the plus 1, but the other 3 terms have to be 2 times something. But we can see that it is, right? We can factor out a 2. That leaves 2kl plus k plus l, and then the plus 1. And again, 2kl plus k plus l, we don't really care what that is, just that it is an integer, and it is. So xy is odd, and we're done. So these were 2 pretty simple examples of direct proofs. The details here are useful to remind yourself how things like that go, but they would be completely different in other proofs, of course. The main thing is just the idea of starting with the hypothesis and getting to the conclusion, and only using the hypothesis and definitions that are known to get to the conclusion. Okay.